Okay, so today we're diving straight into a really interesting paper, AlphaFlow, Understanding and Improving MeanFlow Models.
Yeah, this one tackles a major bottleneck in generative modeling,
Yeah.
specifically for few-step generation. MeanFlow was, a strong contender there.
Right, but it had issues.
Exactly. Powerful framework, but the training, it was just slow, kind of unstable sometimes. And these researchers figure out why. It boils down to the training objective, LMFM.
Okay.
It sort of naturally splits into two pieces. One part focuses on, let's call it trajectory flow matching, LTFM, and the other on trajectory consistency, LTCC.
And the problem?
The problem is that these two parts are essentially fighting each other during training. Their gradients, the directions they tell the model to go, are strongly negatively correlated. We're talking below minus zero point 0.4 similarity often.
Wow, that sounds like a recipe for trouble, like pushing the gas and brake at the same time.
Pretty much. So the solution they came up with is called AlphaFlow.
AlphaFlow, okay.
It's actually a whole family of objectives, which is neat because it unifies a few existing models. But the really clever part, I think, is this curriculum learning strategy they use.
Curriculum learning. So teaching it the easy stuff first.
Sort of, yeah. It's a three-phase approach designed specifically to untangle that gradient conflict. You handle the conflicting parts more strategically, not just throwing them together.
And does it work? What's the payoff?
Oh, yeah. The results are pretty impressive. AlphaFlow consistently beats the original MeanFlow. And their biggest model, they call it AlphaFlow XL2 plus AI, it actually set new state-of-the-art FID scores.
FID scores, okay. The image quality metric, lower is better.
Right. For models trained from scratch on ImageNet 1K at 256 by 256 resolution, it hits 2.58 FID with just one generation step that's 1 NFE.
One step, that's fast.
Super fast. And it gets even better, 2.15 FID with 2 steps, 2 NFE. So what this means for you, the listener, is we're getting closer to really high-quality images, generated much, much faster, and crucially, with less pain during the training process itself.
Okay, let's unpack that a bit more. Why? Why is this focus on few-step generation so critical right now? Let's set the stage.
Well, diffusion models are kind of the kings of image quality at the moment. The results are just stunning.
Yeah, undeniably.
But the big downside, their Achilles heel really, is the speed. Or lack thereof. Generating one of those amazing images often takes dozens, sometimes even hundreds of sequential denoising steps.
Which is fine for research maybe, but not for real-time applications or large-scale deployment.
Exactly. So the whole field has been pushing towards efficiency. First, people tried distillation, basically training a smaller, faster student model to mimic a big, slow, pre-trained teacher model.
Okay, taking shortcuts based on a known good model.
Right. But then came consistency models, CMs. These were a breakthrough because they allowed us to train these efficient few-step generators directly from scratch without needing a pre-trained behemoth.
And MeanFlow fits in there.
Yeah. MeanFlow is a type of consistency trajectory model, a CTM. It was a significant step forward. It really started to close that quality gap between the super fast, maybe lower quality few-step models and those slow, multi-step diffusion models.
It offered more stable training too, right?
Yeah.
And worked better with classifier-free guidance.
It did, yeah. But it was still computationally expensive and honestly a bit mysterious. People knew it worked empirically, but the why wasn't fully understood.
So it was like a black box that gave good results, but nobody quite knew the mechanics inside.
Precisely. And that lack of understanding was hindering progress. You can't really optimize something if you don't fundamentally grasp how it functions or where its weaknesses lie.
So the authors here weren't just trying to build a better model initially. They were trying to understand the existing one first, like scientific detective work.
That's a great way to put it. They needed to analyze MeanFlow's objective function, find the flaw, understand the mechanism, and it was that analysis that directly led them to design AlphaFlow in a principled way.
Okay, let's get into that flaw then. The core technical insight. You mentioned this battle between two components.
Yes. The math here really clarifies things. They showed, through some neat algebraic manipulation, that the MeanFlow objective, LMF-DOL, isn't monolithic. It actually decomposes pretty cleanly into two main terms.
Okay, what are you?
The first one is what they call trajectory flow matching loss, LTFM. Think of this as the part that tries to make the model learn the actual underlying structure of the data generation process, the flow from noise to image. It's got an extra parameter R compared to standard flow matching.
So it's about getting the trajectory right. the path.
Exactly. And the second term is the trajectory consistency loss, LTCT. This is basically a reweighted version of the continuous consistency loss you see in CMs. Its job is to enforce the few-step property, making sure the model's output is consistent across different points along that trajectory.
Right, ensuring that a single step gets you close to where multiple steps would land you.
Efficiency. Precisely. Now, here's the kicker. When they measured the gradients of LTFM and LTCC during training,
They pointed in opposite directions.
pretty much, yeah.
Okay.
Strongly negatively correlated, like we said, often below 9.4. It means that optimizing for one actively hurts the optimization for the other. The model is constantly getting conflicting signals.
Which explains the slow convergence and instability everyone was seeing. It's literally fighting itself.
Exactly. It's a fundamental conflict in the optimization landscape.
So I have to ask, if they're fighting, why not just get rid of one? If delTFM teaches the structure, maybe just use that. Why keep the consistency part, LTCC, if it causes so much trouble?
That's a really insightful question, and the answer gets into the theoretical weeds a bit, but it's crucial. If you only optimize LTCC, the consistency part, it turns out it lacks a critical boundary condition.
Boundary condition,
Meaning it doesn't know what data distribution to be consistent with. It has a huge space of possible solutions, what they call a large optimal solution manifold. Many ways to satisfy LTCC are trivial, like the model just outputting a constant gray image. That's perfectly consistent, but completely useless.
Okay. So LTCC says be efficient, but doesn't say be efficient at making realistic images. It needs guidance.
Exactly right. Now, conversely, LTFM, the flow matching part, implicitly provides that necessary boundary condition. It anchors the model to the real data distribution. But its optimal solution manifold is very narrow and specific. It's hard to find.
So LTCC knows the target, but it's a small target. LTCC doesn't know the target, but it's easy to satisfy in some way.
You've got it. And when you try to optimize them together, the optimization process naturally gets drawn towards the big, easy region defined by LTC, pulling the model away from the small, difficult, but correct region where both losses are minimized.
It gets distracted by the easier task, like trying to find a needle, LTFM, in a haystack, and the optimization just keeps getting lost in the hay.
That's a perfect analogy, and this directly explains that 75% problem people talked about with the original MeanFlow.
Right, you mentioned that earlier, 75%.
Yeah. To stabilize training, the original MeanFlow paper ended up dedicating a massive 75% of the training computation to this specific border case flow matching loss, 11A, where the parameters $2 are equal.
Why that specific loss?
It essentially acted as a kind of stand-in, a surrogate loss for the problematic LTFM. It provided the necessary boundary signal, but crucially, interfered less with the gradient of LTCCA. It was a workaround.
But really extensive workaround. 75% overhead is huge.
It's enormous. Basically, they were papering over this fundamental gradient conflict with sheer computational brute force. It worked, kinda, but it was incredibly inefficient.
Okay, so that inefficiency, that brute force approach, is exactly what AlphaFlow aims to fix by tackling the root cause, the gradient conflict. Let's pivot to the solution then. How does AlphaFlow actually do it?
Right. The first clever thing is the AlphaFlow objective itself. They define it as this general family of objectives, and it's controlled by a single parameter, alpha, which represents the consistency step ratio.
Alpha. Okay, what does that parameter do?
It basically lets you smoothly interpolate between different training regimes. It provides this elegant unification. For example, if you set alpha $1, the objective becomes pure trajectory flow matching, LTFM.
So focusing only on the structure part.
Exactly. If you let alpha approach 0, you recover the original MeanFlow objective with its mix of LTFM and LTCC.
So it connects the two extremes.
And not just those. They show that other approaches, like shortcut models, fit neatly into this framework too, corresponding to alpha 12-2. So it's a really nice theoretical consolidation.
That's cool. But unification alone doesn't solve the gradient conflict, right? How do they use this alpha parameter?
That's where the curriculum learning comes in. It's outlined in their algorithm too. Instead of just picking one alpha or trying to optimize the alpha right or case directly, they use alpha to guide the training through distinct phases.
Okay, walk me through the phases.
Phase 1 is pre-training. Here they set alpha level 01.
So pure trajectory flow matching.
Right. They focus entirely on LTFM at the beginning. Why? Because LTFM, while having that narrow manifold, is a lower variance objective compared to the consistency loss. It provides a more stable signal early on.
So nail down the structure first, Build a solid foundation before introducing the tricky part.
Exactly. This pre-training phase quickly converges the model towards that correct narrow manifold, giving it a good estimate of the noise-to-data mapping.
Makes sense. What's phase 2?
Phase 2 is the transition. Here, alpha isn't fixed. They gradually decrease it from 1 down towards 0.
Gradually.
They use a smooth sigmoid schedule, so it's not a sudden jump. This allows the model to smoothly transition from the high bias, low variance regime of pure flow matching, alpha dollars, towards the low bias, high variance regime of mean flow, alpha right arrow dollars.
So you're slowly introducing the LTCT component and its associated challenges, but hopefully the model is stable enough from phase 1 to handle it.
That's the idea. You gradually blend in the consistency objective without destabilizing the whole process.
Okay, and the final phase.
Phase 3 is fine-tuning, where alpha gets very close to 0, effectively optimizing the mean flow objective. But here's the key. Because the model already has a strong structural foundation from phase 1 and was gently guided through the transition in phase 2.
It doesn't need that massive 75% computational crutch anymore, that LoFM surrogate loss.
Precisely. The reliance on that expensive surrogate loss is drastically reduced. The model can now handle the conflicting gradients of the near mean flow objective much more effectively because it started from a much better place. It's a huge win for training efficiency.
That's really elegant. Addressing the core problem allows them to remove the expensive workaround.
Exactly. And some implementation details really show this strategic thinking. For instance, they found clamping alpha as important as it gets very close to 0.
Clamping, just stopping it from going all the way to 0.
Yeah, they found empirically that an optimal clamping value, eta, was around alpha 5 times 10 through 3. Going lower could still lead to some instability, so this final little nudge helps.
Interesting. And you mentioned the loss weighting was also improved.
Yes. Original MeanFlow used an adaptive weight based just on the size of the change vector, delta dol. AlphaFlow derived a new weight. Omega alpha delta 22 plus cell.
So the weight explicitly depends on alpha.
Right. As alpha changes during the curriculum, the loss weighting automatically adapts. This provides much smoother and more principled stabilization compared to the original adaptive weight, especially during that crucial transition phase.
Okay, the theory and the strategy sound solid. Let's talk results. Does this actually translate to better performance on benchmarks like ImageNet? What do the numbers say?
The numbers are definitely convincing. Let's look at ImageNet 1K at 256 by 256 resolution using their DTIT XL2 model architecture. The standard AlphaFlow XL2 model trained for the same duration as the original MeanFlow.
Okay, apples to apples comparison.
Right. It achieves an FID score of 2.95 in just one step, 1 NFE. Remember, lower FID is better. The original MeanFlow XL2 got 3.47 FID.
So 3.47 down to 2.95. That's what, like a 15% relative improvement?
Exactly. A solid 15% improvement in image quality generated just as fast, trained using the same amount of overall compute.
That's significant. And you mentioned a state-of-the-art result.
Yeah, if they take that model and fine-tune it a bit longer, they call this one AlphaFlow XL2, plus it pushes the 1 NFE FID down to 2.58, which, as far as few-step models trained from scratch go, was the new state-of-the-art at the time of the paper.
2.58 FID in one step is really impressive for a from-scratch model. And what about the curriculum itself? Did they show that the phases actually matter?
They did. They ran ablation studies, varying things like the length of the pre-training phase, alpha dollar ones. The results clearly showed that longer pre-training, spending more time just on LTFM early on, consistently led to better final FID scores.
So it really concerns the strategy. Nail the foundation first.
Absolutely. And having a smoother, longer transition phase also helped. It validates the whole idea of separating the optimization concerns rather than tackling the conflict head-on from the start.
And did they confirm the efficiency gains? Did they actually need less of that expensive AlphaFM loss?
Yes, that's another key result. They found that AlphaFlow achieved its best 1 NFE performance when using a flow matching ratio of only 25%.
25%, down from 75%.
From 75% in the original MeanFlow implementation. So they effectively cut the reliance on that specific computationally heavy surrogate loss by 2/3. That's a massive practical saving in training cost.
Huge win for anyone actually training these things.
Hmm.
Before we wrap up, any quick notes on the sampling process itself? Anything interesting when generating the images?
Just a small nuance, mostly for the technical folks listening. When they were generating images with two steps, 2NFE, especially with the larger DIT-XL2 models, they found that consistency sampling generally worked better than using standard ODE numerical solvers.
Ah, so using the model's built-in consistency mechanism was more effective than an external solver for that two-step generation.
Seems so, yeah. They got their best 2NFE FID scores at 2.15 number using consistency sampling, particularly when the intermediate step was around $2.04. So just a small tip if you're implementing or using these models.
Good to know. Okay, let's try and summarize the core takeaway for everyone listening.
Sure. I think the main point is this. MeanFlow was powerful but flawed due to this internal conflict in its training objective. LTFM wanted structure, LTCC wanted efficiency, and they fought each other.
Right. And AlphaFlow's big contribution was first, scientifically diagnosing that conflict by decomposing the loss, and second, designing a smart curriculum learning strategy around the alpha parameter to manage that conflict.
Exactly. By handling the structure part, LTFM first, then gradually introducing the consistency part, LTCC, they could train better models more efficiently, dramatically reducing the need for that costly 75% surrogate loss workaround from the original MeanFlow.
So for you, the listener, this means we're getting state-of-the-art few-step generative models that produce higher quality images faster and are significantly cheaper and more stable to train. A big step towards practical, fast, high-fidelity generation.
Couldn't have said it better myself. And it leaves us with a really interesting thought, maybe for future work.
Oh yeah, what's that?
Well, the analysis showed pretty clearly that the flow matching component, LTFM-DAR, implicitly provides the boundary condition that the consistency component, LTCC, desperately needs to avoid collapsing.
Right, the implicit guidance.
But why does this implicit condition work so well? Why is it seemingly more effective, or at least easier to integrate during training, than trying to impose an explicit boundary condition on consistency models? There's probably some deep theoretical reason there.
Ah, so digging into the mathematical reasons behind why that implicit guidance is so effective could be the next frontier. Understanding that could lead to even better, more stable consistency models down the line.
Potentially, yeah. If we really understood the mechanics of that implicit boundary, maybe we could design objectives that are even more stable and efficient from the get-go. It's a compelling theoretical question prompted by this very practical work.
Definitely something for researchers out there to chew on. And for everyone else, if you want to get your hands dirty with AlphaFlow, the authors did make their source code and checkpoints publicly available, so go check it out.